myself, Subhadeep. I'm a PhD student at IIT Kharagpur, and today in this session we will see how we can use Sklearn for performing name-based classification. Okay. So the name-based classification is already covered in the class. So I hope that you already have some idea about the mechanism of the classification. So can anyone briefly tell that what is name-based classification, how it's different from the other classifiers?
It is based on Bayes theorem, sir. It is
Yeah.
coming from probability and statistics concept.
Okay.
It's always based on conditional probabilities.
Yeah, it's based on conditional probability, but so there is a special, simplification or assumption taken in name-based classification. So what
Yes,
is that assumption?
that assumption. We need to take every pair of features, sir. We need to compare them.
We need to take every pair of features. Is that you meant?
Yes, sir.
Not
As
exactly.
of my knowledge. Okay.
Okay, so actually, it's not. It's the assumption is called the conditional independence assumption. So, given the class level, each feature is assumed to be independent of one another. Okay. So, given the class level, each feature is independent of other features. Okay, so that is called the conditional independence assumption. Okay, so let me explain. So first of all, the name-based classifier is a generative classifier, which means that it's 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 model the probability of x, the probability of x, that is probability of the features given the class. Okay, so it's model that probability and then uses the Bayes rule to calculate or to obtain the probability of y given x. So this is the probability of y given x, that is what we are interested in, because it's a classification problem, right? So in classification problem we want the probability of the label given a input data, right? For some input data we want what will be the probability of a particular level or particular class. That's what we want, right? So we want this problem. Okay, we want this probability of y given x, right? But we do not directly model this probability y given x. Okay, so rather we take some form of the probability distribution of x given y. So given the class level, so for class 1 there is some probability distribution for the input data. Okay, similarly for class 2 there is a probability distribution for the input data. Okay, right? So we model that probability of x given y. Okay, and then using this Bayes rule we calculate, we represent or compute or obtain this probability of y given x in terms of probability of x given y. Okay, so can anyone give some examples of this probability of x given y? Can anyone give any example of this? So suppose we have a single dimensional data, x is just one dimensional, right? So in that case, and it's a real number, can you tell me that what kind of probability distribution we can assume for that x? Just think, just see, given y, x, what I said is that x is a single dimensional real data. So name a distributions which which models the real numbers. Yes, any distribution over real numbers. There are many. Any distribution over real numbers. Huh? Any distribution over real numbers. The most easiest distribution is the Gaussian distribution. So do you know Gaussian distribution? Do you know Gaussian distribution?
No, sir.
So what kind of probability distribution are you familiar with?
Binomial distribution.
Huh? Pardon?
Binomial distribution, normal distribution.
Binomial normal distribution, you know, right?
Yeah.
Normal is same as Gaussian distribution. It is sometimes called Gaussian distribution. It is sometimes called normal distribution. Okay. So Gaussian means it's normal distribution. Binomial, normal, any other? Bernoulli distribution. There are many, right? So a distribution over real number is a normal distribution. Normal distribution is a distribution over real numbers, right? So one way to model x given y is a normal distribution. So suppose there are two class 1 and class 2. So we can assume that for class 1 the data is being generated using one normal distribution, and for class 2 the data is being generated from another normal distributions, right? So like this. So suppose x, the probability of x given y is equal to 1, we can assume that it's being generated from the Gaussian distribution with some parameter, square root of 2 pi sigma 1 square e to the power minus x minus say some mu 1 square pi 2 sigma. Okay, so this is a Gaussian distribution with parameter mean mu1 and standard deviation sigma 1. Similarly, for class 2 the data is being generated from another distribution with the from the normal distribution with a different parameters, or with a different mean and standard deviation. Okay, so suppose this is being generated by 2 pi sigma 2 square e to the power minus x. Okay, so there are two different distributions from which the data is being generated. Okay, so now if x is, so in this case x is one dimensional. If X is two dimensional, then data might be generated from two dimensional from some distribution over two dimensional data. For example, it might be for two dimensional, it might be a multivariate normal distribution. Is anyone familiar with multivariate normal distribution? It's something like this. Say probability of x is a vector given y is equal to square root of 2 pi determinant sigma. I think there is some kind of 2 to the power d. So suppose x is a t-dimensional vector, x1 xg x. Oh no, it's why it's not working. x0 to x d minus 1. Okay, so in that case it will be e to the power minus half of x vector transpose sigma inverse x vector. Oh, x minus mu. Mu1 transpose sigma 1 inverse x minus mu 2, something like that. So in this case your mean will be a mean vector of d-dimensional vector which is called mean vector, and the sigma will be replaced, this sigma 1 and sigma 2 will be replaced by a covariance matrix called capital sigma 1 and capital sigma 2. Okay, so the problem with this kind of assumption is that multivariate Gaussian distribution is that here the number of parameters is quadratic in the feature dimension. So here the feature dimension is d, so number of parameter is in the order of d square. So here the number of parameter is much larger. So in this case, and in machine learning, what happens if your some machine learning model has more number of parameters, then it requires more number of data to estimate that parameter with some accuracy. Okay, so that is the problem with the machine learning. So it is sometimes preferable, especially when the amount of data is very less, you use a model which has very less number of parameters. Okay, so Naive-Bayes is one such model. Where what it is done, it assumes that for each class, for given each class, the features are independent. So in this case, if we in this case, say if we take a multivariate Gaussian assumption, the number of parameters will be the quadratic in terms of the feature dimension. So here we can take, if we take a Naive-Bayes assumption, we will assume that the features are all independent of each other. So in that case, each of these features x1 to xd minus 1 will be a univariate normal distribution with some parameter mu say 1d and mu say yd and sigma yd. Okay, so each of these features will be a univariate features. Okay, so in that case, so each of them will requires two parameter mu say 1 y plus sigma 1 y. Similarly, this case mu dy sigma dy. So each of those will have two parameters. So as a result, total number of the parameters of the model will be something called 2 into d. Okay, so which is linear in d, so in this case, in naive Bayes, what we assume that this probability of x given y is nothing but the multiplication of individual probability of xi given y. So this multiplication comes from the conditional independence assumption. Okay, so as a result, the number of parameters of the models gets reduced a lot. Okay. So is it clear? Students, is it clear?
Yes, sir.
Okay, so now that is the basic idea behind naive Bayes classifiers. Now we will basically look into some of the examples of different kind of naive Bayes classifiers. So in general, naive Bayes is kind of computes these kind of terms. Is probability of y. What can anyone tell? What is this probability of y here? Can anyone tell what is this probability of y? Probability of y is basically this is basically marginal probability of y, that is which is basically nothing but what is the fraction of the data belongs to class say y is equal to 1, or what of the fraction of the data belongs to class 2, something like that. So there are say C classes 1, 2 up to C. Then probability of 1 means that what is the fraction of the data belongs to class 1. Probability of 2 means what is the fraction of the data belongs to class 2, something like that. Okay, so it's called the marginal probability. Okay, it's called the marginal probability. Okay, so now this is okay. This follows some kind of categorical distribution, and then you have to model this individual features, conditional probability of individual features pxi given y. Now you can, depending on the data, you can use different kind of distribution to model this conditional distribution of the features. Okay, for example, if you know that x is some kind of real value, then you can model this distribution probability of xi given y using some distribution which supports real numbers like normal distribution. You can use, for real x you can use normal distribution or Gaussian distribution to model this xi given y, and in that case the naive Bayes classifier is called Gaussian naive Bayes distribution. Okay. Similarly, if your xi's are say 0 1 value, some binomial data, say it can be either 0 or 1, in that case you can model this probability using some kind of distribution which supports binomial data, like you can use Bernoulli distribution to model this data. In that case the distribution is called the naive Bayes algorithm is called the Bernoulli naive Bayes. Similarly, if this xi can be some count like 1 2 3 like that, count of some events, something like that, in that case you can model this probability using some kind of multinomial distribution. In that case the naive Bayes algorithm called multinomial naive Bayes. Okay. Similarly, if these xi are categorical data, in that case you can use categorical naive Bayes. Okay. So we will basically look into some of those examples, and also note that sometimes you might want to, your data is something like that some of the features are real numbers, some of the features are binomial data, some of the features are say some count data, and some of the features are categorical data. Then you can use the mixture of those kind of features, those kind of naive Bayes algorithm, like the features which are really, for those you can use Gaussian model. The features which are binomial you can use Bernoulli model, something. So you can do some kind of mixture of those kind of modeling. Okay. So first we will look into the Gaussian naive Bayes. In Gaussian naive Bayes, each of these, so it's basically is applicable for real data. Okay. So in this case basically, and which can be both positive and negative or something like that. Okay. So in that case basically each of these probability xi given y is modeled as a Gaussian distribution with some parameter. One parameter is called theta and the other one is called the sigma. Theta is basically the mean of the Gaussian distribution, and sigma is the standard deviation of the Gaussian distribution. Now can anyone tell that for a d-dimensional features how many total parameters will be there, or how many total parameters will be there for a Gaussian naive Bayes? Can anyone? Please response. Yes, any guess? See, if we want to use this Gaussian naive Bayes, then how many probability distribution will be? Do we need to fit? So I'm giving some examples. So suppose my features is something like this. Say there are two features, x1, x2. Okay. There are two features, and say two features, and there are say some data, say 0.5, 0.3, minus 0.2, 0.1, minus 0.3, 0.25, 0.6, 0.7, something like this, and say there are two class. The first two examples belongs to class 1, and the second two examples belongs to class 2. Okay. Now tell me that how many Gaussian distribution do we need to in a Gaussian naive Bayes? Okay. How many Gaussian distribution do we need?
2.
For which data? So how can you tell me why 2? So which data will be belongs to the distribution 1 and which data will belongs to distribution 2?
For class 1, maybe one of the distribution, class 2 other.
No, but we are taking basically naive Bayes assumptions. So we need different distribution for each of the features also. For each of the features also we need different distribution. So how many total distribution do we need? Say for x1 there will be one distribution, for x2 there will be one. So in total how many distribution do we require? So see, there will be total of 4 distributions. Something. So we need one distribution to feed this data, one distribution to feed this data, one to feed this data, one to feed. You understand? Since we are taking the naive Bayes assumption, so the distribution used for x1 will be different from the distribution used for x2. So for x1, for each combination of class and the features, we will need one distribution. So since there are 2 features and 2 classes, then we need 2 into 2, 4 distribution. Okay?
So you mean for x1 2 distribution and for x2 2 distribution?
Yeah, for x1 one distribution will be required for class 1 and the other distribution will be required for class 2. Similarly for x2 one distribution will be required for class 1 and the other distribution will be required for class 2. Okay, so if there are say k classes, then for each feature how many distribution do we need? So instead of 2, suppose there are k classes, then for each feature, for a single feature, how many distribution do we need? Come on, I have just told you.
2k.
No, for each feature, for a single feature, suppose there is only x1, then how many distribution do we need?
K classes, K distributions.
K classes, K distribution. Okay, now say K classes and D features, then how many distribution do you need? In total, K classes, D features. So in total how many distribution you need? See, for each features we need K classes, K distributions. So now there are D features. How many?
K into D.
K into D, right? K into D distributions we need. Okay. Now we need to think, if we want to calculate the total number of parameters, we need to think that how many parameters do we need for each distributions. How many? So if we are using Gaussian distribution, then how many parameters do we need to represent a Gaussian distributions? How many parameters does a Gaussian distribution have? Huh? How many parameters?
Mean and variance.
Mean and variance. Then how many parameters? How many parameters? You just told mean and variance. And how many parameters?
2
2.
into KD.
Okay, so then the total number of parameters is 2 into k into t, but it's not enough. Now say, oh, okay, now, so this is the total number of parameters in this part, and we need some parameters to represent this condition, this marginal probability, marginal class probability or class prior. We need some parameters. So says there are C classes, then how many parameters do we need to represent this distribution probability of y, this class probability? How many parameters will be there? So there are C classes. How many parameters are there in this distribution, the marginal distribution? How many? It's a categorical distribution, right? So categorical distribution with C classes. So how many parameters are there in that distributions? You need C minus 1 parameters. So each one will represent the C minus 1, each one will represent, say, the first parameter will denote the probability of class 1. The second parameter will denote the probability of class 2. Similarly, the C minus 1th parameter will denote the probability of class C minus 1. Now, what will be the probability of class C? That will be calculated by 1 minus sum of the rest of the probabilities. Okay, that will give the probability of the last class. Okay, so you need C minus 1 parameter. So in this case, in this examples, the total number of parameters in this model will be 2 into k into d plus k minus 1. Okay, so that is the total number of parameters in the model. Now you can compare with the model which assumes a multivariate Gaussian distribution. In that case, your number of parameters would have been k plus something like d into d minus 1 by 2 into k, some plus k minus 1. Oh, sorry, this is d minus something. So you can see that there is a quadratic term in this in this equation. So if d is large, then the total number of parameters will be very large. Okay, so it's a lot of reduction in the number of parameters. Okay, so now just I'm coming to the examples. So for performing Gaussian name base, you can basically use this module, Gaussian name base. Use this module to perform the Gaussian name base. Okay, so first I am importing the modules, and then I am generating some sample data. Okay, and then I am fitting the Gaussian name base model, training the Gaussian name base model, and then I can use this prediction functions to predict on some new examples, something like this. Predict probability, predict log probability. Okay. Now you can look into the parameters also. Okay. Okay, so okay, now let us come to the Bernoulli name page. Okay, so uh, first I will start with a examples of text classification. Suppose our task is that given a sentence, we need to classify the sentence into two classes, class 1 and class 2. So here is some example sentences like this is the first document which belongs to class 1, and the second sentence is this document is the second document which belongs to class 2. Then the third example is that and this one is the third one which belongs to class 2, and the last example is this the first document and it belongs to class 2. Okay, so there are 4 sentences and which belongs to 2 classes. Okay, now if you are familiar with this binary bag of words feature representation, then you might know that one way of converting this corpus or this data into some feature matrix with binary variable is something like that. So you generate features corresponding to each of the words of the documents. So suppose in this corpus, this 9 words appears and document first is 1, second, the third, this. So this 9 words appears. So each of the words will be presented as a features. So there will be total of 9 features. Okay. Now what you will do? You will take the first examples and set the bit corresponding to a particular features as 1 if that words belongs to that example. For example, in this case, in the first examples, the word document belongs to the first examples. So we will set the entry corresponding to this feature document as 1. Similarly, the word first belongs to this sentence, so we will set this bit as 1. Okay. On the other hand, the word and do not appear in the sentence, so we will set 0 for the for and. Okay. Similarly, the word second do not appear in the first document, so we will set 0 corresponding to second. Okay, so in that way we can create the feature matrix. Okay, now in this kind of feature representation, the entries of the feature matrix are either 0 or 1, or we may say that it's the binary data. It either 0, all the features are binary. It can be either 0 and 1. Okay, so when the data is binary, then we can model this conditional probability of xi given y as a Bernoulli distribution, something like this. Okay, so we can model this as a Bernoulli distribution. Okay, with parameter theta I, with some parameter theta. Okay, so for each class and each feature ID there will be 1 theta. So in this case the total number of parameter representing this x given y part will be the total number of features multiplied by total number of classes. Okay, so we can basically, you can look into it in more detail later. Okay. So here is an examples of Bernoulli name page. Then I can okay. So in this way you can basically train a Bernoulli name page. Now there is some certain issues with this. Okay, so for examples, I am just giving one issue is that, say, in this uh, 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 so let me move into this. Okay, so suppose in one example, so in a one Bernoulli name page, so suppose some feature, there is one features called x1, one is x2, and say let the corresponding 0 1. Okay, now this, okay, now this 2 belongs to class 1, and this 2 belongs to class 2. Okay, now can anyone tell that what will be the probability of x is equal of probability of x1 is equal to 1 given y is equal to 1, and then probability of x1 x2 is equal to 1 given y is equal to 1, probability of x1 is equal to x is equal to 1, y is equal to 2, probability of x2 is equal to 1 given y is equal to 2. Can anyone tell what will be the probability? First tell me what will be the probability that probability of x1 is equal to 1 given y is equal to 1. What will be the probability? Anyone?
Is it 0?
It's 0, right? Okay. And what will be the probability of x2 is equal to 1 given y is equal to 1?
Point 5.
0.5. Then probability of x is equal to 1 given y is equal to 2.
1.
1. And what will be the probability of probability of
5.
0.5? Okay, now say suppose there are another examples, otherwise won't be. Okay, probability of x3 is equal to 1 given y is equal to 1, probability of x3 is equal to 1 given y is equal to 2. What will be this probability? What will be these probabilities?
One and 0.
1 and 0. Right. Okay. Now suppose we are given a new examples to predict. Okay. So the new examples is, say, suppose 1 0 1. If there 1 0 1. Okay. Now can anyone tell that what will be the probability of, say this is some x bar, what will be the probability of y given 1 given x bar and probability of y equal to 2 given x bar? How it will be calculated? I am just telling the formula. So it's something like probability of y is equal to 1 multiplied by probability of x bar 1 is equal to 1 given y is equal to 1 multiplied by probability of x bar 2 is equal to 1. Oh, sorry. 1 is equal to 2 given y is equal to 1 and probability of x bar 3 is equal to 1 given y is equal to 1. Right? This will be the probability, right? This will be the probability, right? Are you fine with this probability? See, the first bit of x bar is 1, so we need to multiply probability of x1 probability of x1 is equal to 1 given y is equal to 1. Right? First bit is 1, so we need to multiply probability of x1 is equal to 1 given y is equal to 1. Then the second bit of x bar is equal to 0, so we need to multiply probability of x2 is equal to 0 given y is equal to 0. And the last bit of x3 is equal to 1, so we need to multiply probability of x3 is equal to 1 given y is equal to 1, right?
Yes, sir.
Okay. And what will be the probability of this probability? This is half, we know. And probability of x1 is equal to 1 given y is equal to 1 is 0. So it's 0. Okay. Multiplied by probability of x2 is equal to 0, y is equal to 1. x2 is equal to 0, y is equal to 1. x2 is equal to 0 is basically 1 minus this. 1 minus this one, so 0.5. 0.5 multiplied by probability of x3 is equal to 1, y is equal to 1. x3, so this is 1 again. So it's 0, right? Right? Are you okay with this? Okay. Now I calculate the second probability. Probability of y equal to 2 given x1 is equal to probability of y equal to 2 probability of x1 is equal to 1 given y is equal to 2, probability of x2 is equal to 0 given y is equal to 2, and probability of x3 is equal to 1 given y is equal to 2. Okay, now I'm just putting the value. Y is equal to 1, x2 is equal to 2 is 0.5, x2 is equal to 0, y is equal to 2, x2 is equal to 0, y is equal to 0.5, and the last one x1 is equal to 0, y is equal to 2, x1 is equal to 0, y is equal to 2 is 0, it's 0, so it's again 0. So now see that for these examples I am getting both of those probability as 0. Okay, so can we compare that which one is the greater and which one is less? Because if I want to determine in which class this new examples belongs, can we compare? Because for both of the classes the probability is 0. So to which classes the x1 x bar belongs? Can we say? Can we say? Because I am getting the probability as 0 all the time. Can we say in which classes the data, the new sample belongs? Can we say? We can't say, right? So
No.
yeah, so these kind of problems arise because the most of the entries are 0. Most of the entries of in this matrix, feature matrix, are 0, and when there is one entry 0 entry, then what happens that the probability of that particular features, seeing that features given the class, becomes 0, and that 0 probability get multiplied with the rest of the probability and makes the final probability 0. You understand? So what is happening here is that in this case we are multiplying the individual probability of individual features, right? If sum of the probability becomes 0, then the total probability becomes 0. You understand? So each individual probability, we are multiplying each individual probability. Okay, if one of those becomes 0, then the whole probability becomes 0. And when there are lots of 0 entries in this matrix, feature matrix, it is highly likely that some of the probability of some of the features will become 0. When there are lots of 0 entries, and it's very usual, it's very common that most of the entries of this feature matrix will be 0. Okay, as a result, the whole probability becomes 0, and once the probability becomes 0, we can't compare, because for all the classes we are getting the probability as 0. So we can't determine in which class the samples belongs. Okay, so to solve this problem, what it is done is that we add a small entry with small positive numbers to each of these numbers. So actually we add a small numbers to the count of each of the features and each of the classes, basically. So actually to determine this theta, what we need to do is basically we divide we calculate the fraction of times, or the fraction of examples for which the feature is 1. So this number NYI is the number of samples in which of class Y in which the feature Xi is 1. So this NY is basically nothing but number of samples of Y, number of samples of class Y in which the feature Xi is 1, and NY is the total number of samples. So to calculate the theta IY, we basically need to divide NYI by NY, which is nothing but the fraction of samples of class Y in which the feature Xi is 1. Okay. Now, if we basically just calculate theta IY in that way, we will get theta IY, lots of theta IY 0. So to avoid that, what we need to do is basically what it is done is basically it is called some kind of smoothing. We add a small positive numbers to each of these entries. Okay, we add a small positive numbers to each of these NYI. Okay, so in that way we can calculate theta I, and in that case, even if NYI becomes 0, the whole probability will not become 0. Okay, you understand this? So in suppose for some yi, the NYI is 0. Since we are adding some small numbers alpha with NYI, the whole fraction will no more become 0. Okay, so it will be some non-zero, small non-zero quantity. Okay, you understand? So this is called smoothing. This is called smoothing.
So what will be the value of that alpha?
Okay, so generally it's a hyperparameter. You can set it to small value. There are some standard value, like if you set alpha is equal to 1, then the corresponding smoothing is called Laplace smoothing. So in Laplace smoothing, alpha is 1. But you can set it to some other small value as well. Okay, generally you can consider this parameter as a hyperparameter. Okay.
So if the distribution is Gaussian, the same condition will happen, or what?
Now in case of Gaussian, theoretically it won't happen, because Gaussian distribution does not have zero probability. It does not assign zero probability to any of the sample points, any of the real numbers. So you take any Gaussian distribution and ask and take another any real numbers and ask what is the probability of getting these real numbers from this Gaussian distribution. You will always get a non-zero value, though this value can be very small and close to 0. But in case of Gaussian distribution, this kind of situation does not appears, because we estimate the parameters of the distribution from the data, right? Now if some data is within the data, if some value is in the data, then that data will have some non-zero probability. So for Gaussian distribution, these kind of problems will not appear, because suppose you are fitting some Gaussian distribution to this data. Okay, in this case, since this data is being used to fit the data, so this data will have some non-zero probability of getting. Okay, so in case of Gaussian distribution, generally this kind of situation do not appear. It might appear in some pathological cases, but generally do not appear. This kind of problem appears in case of sparse data, like when the features matrix are sparse. In those kind of scenario, these kind of problems appears. Okay.
Okay, sir. Okay.
Okay. Now there are another problems. The another problem is this. What we are doing is basically we are calculating the class probability. Probability of some y given x, y say probability of x1 given y dot xd given y, right? We are basically multiplying many probabilities to get the final probability, right? So that's what we do. That's what this formula is saying. So you basically multiplying many probability to get the final value. Okay. Now what if, say, suppose on an average all these probability are something like this, 0.1, 0.1, 0.1, something like this. Then what the resultant value will be something minus 0.5 in to the power d, right? D plus 1, or it will be something 10 to the power minus d plus 1. Okay, something, right? It will be order of something like this. Okay, the probability you will be calculating will be order of something like this, 10 to the power minus d plus 1, right? Yes or no? Do you agree?
Yes, sir.
Yeah, okay. Now see, suppose d is say thousands, and it's very common. It's very common to have some thousands dimensional features. Then what will be this value? This value will be 10 to the power minus thousands and 1. 10 to the power 1001 cannot be represented using some kind of some floating point representation. The usual floating point like double precision or single precision floating point numbers. Using double precision or single precision floating point numbers, you can't represent these numbers because it's 10 to the power thousands. So it's too small. It will underflow. It will give underflow error. Okay. So as a result, so suppose you have say probability of y1 given x, probability of y2 given x, and you will get a underflow for this value nan. If you do use Python, you will get nan, and if you use Python, you will get nan, and you can't compare these two numbers. Understand the problem? You understand the problem? If you multiply too many small numbers, the resultant number becomes so small that the machine will give underflow error. It won't be able to represent the number using some single precision or double precision floating point number. Is it clear? The problem is clear?
Yes, sir.
Okay. Then how to solve this problem? Okay. So it is solved in this way. See, for classification we don't need the exact probability. What we need to do is basically we need to able to compare two or more than two probabilities. Like for examples, we have basically probability of y1 given x, probability of y2 given x, probability of yk given x, so yk given x. Okay, so we don't need their exact value. What we need to is that somehow we should be able to compare their values, whether one is greater than the other. So that's what we need. Okay, so for that, so suppose we want to compare probability of y1 given x and probability of y, sorry, y2 given x, whether one is greater than the other. So it can be well compared if we, even if we take log of both the sides. Right? It can be compared like this. So if this holds, probability of y1 given x greater than probability of y2 given x, then it must also hold log of probability of y1 given x greater than log of y2 given x, and vice versa. If this holds, this also holds. This, if the second line holds, the first line also holds, right? Do you agree?
Yes.
Okay. Now see what will happen is something like this. Oh, sorry. Now see, now you put the expression of log of this conditional probabilities. Probability of y1 multiplied by I is equal to 1 to d probability of xi given y1. Okay, so in this side this one, this side will be, so it's basically log probability y2 1 to d probability xi given y2. Right? So now what will happen, because of the log, the multiplication becomes the addition, so it will be